Okay, so let's start today's session. Good afternoon, everyone. As you know, this is the last session for this NPTEL course, Solid State Physics. The course instructor for this course was Professor Amal Kumar Das from IIT Kharagpur, and I have been the PMRF TA for this course. I am from School of Physics, University of Hyderabad. And in this extra session, we can discuss some of the superconductivity things. So, if you saw in this week's lecture, most of the things were related to dielectric, and there was one lecture on superconductivity. So, maybe for your course, it's not much weightage is given to superconductivity topic. So, we will also not delve into too much of details. But I have brought a lot of questions based on magnetism and superconductivity. Yeah, when they will come, we'll see. Okay, so yesterday, I mean, for this week, we had discussed things on dielectric properties of solids, and there were a lot of similarities between when we deal with magnetic properties of materials and then dielectric properties. Like we have magnetic moments the same way we have dipole moments, but like magnetic moment was between north and south pole, you can understand, or one end of magnetic moment is usually any say bar magnet, or even when we have a current carrying conductor, we know at one face it will be north pole, on opposite face it will be south pole, and in a bar magnet also we have north and south pole. So when we talk about magnetism or magnetic properties, we were talking about the fields, magnetic fields originating from North Pole ending at South Pole. Whereas when we talk about dielectric properties or polarization, and here we talk about electric dipole moment. And that is between separation of positive negative charges. So, and we had seen we have basically three types of origin of this electric dipole moment in a solid. One was electronic, another was ionic, and third was orientational, whereas already some permanent dipole moment is there. So in electronic and ionic, what we were seeing, we had like in electronic, we were talking about that atom, any random atom or molecule, where we know in an atom all the positive charge is at the center in the nucleus, and then in the orbits we have electron revolving, we can say in classical mechanics, or probability of finding electrons when we talk in quantum mechanics, but electron or negative charges around this center. So there may be two in the first shell, and there may be, depending on what is the atomic number, other in subsequent shells. So overall we can see the center of all this negative charge will be somewhere in the center. So positive charge center and negative charge center coincide. So there is no net dipole moment here. But when we apply electric field, then since we know electric field will exert force on the positive negative charge, and thus because of that electric field they will experience some force, and also depending on what is the sign of that charge, positive or negative, the direction in which the force is exerted will also change. For positive charge, the positive charge goes along the direction of electric field, and negative charge goes opposite the direction of electric field. But here when we talk about atom, we say that since mass of neutron is 1000 times more than mass of electron, mass of electron we know is of order of 10 to the power minus 31 kgs, and mass of neutron is of order of 10 to the power minus 27, 28 something. So it's like 1000 times heavier than electron. So when we apply electric field, we say that positive charge or the neutron or nucleus is at the center. Instead, we say the electron charge, cloud charge is what is shifting because they are lighter. But eventually, eventually what we get is either of these are moving, it's fine, because as soon as there is some distance between the positive center and the negative cloud center, so we get electric dipole moment, the charge and the distance. And the direction of electric dipole moment is from negative to positive direction. So this is what basically happens in presence of electric field. I mean, this is how a material responds to. But what kind of material when we are talking about dielectric materials? All this property of dielectricity, because otherwise, if the material is not dielectric, means it's a good conductor, electrical conductor, not thermal we are talking about. We are talking about good electrical conductor, means its resistance or resistivity is very small. Then electric field is voltage, right? It's just voltage per unit distance. So when we apply voltage, we know in any circuit or anywhere, if we apply voltage, the electrons will start flowing. But here, because resistance is very high, so electrons don't flow, and thus that's why dielectric materials behave like capacitors, because charges just accumulate on both sides if we apply voltage. So dielectric properties is like, dielectric materials are the materials in which when we apply electric field, this electric dipole moment and all these electronic ionic orientational origin of electric dipole moment happens. Also, as we had discussed, that not all types of magnetization is shown by single material. The same way, not all materials show all these three types of electric dipole moment. Some may be showing orientational, some may be showing electronic, some may be showing ionic, or one or two combinations of these. So this was, and then yeah, basically these were the things discussed, and then some portion was on Clausius-Mosotty relation that also we discussed last session. What is its importance? And there were major, yeah, last session we also discussed about domains in magnetic materials, because we were talking about all different types of magnetic materials, and then this was very important aspect, especially when we are talking about ferromagnetic materials, that there is something known as domain, which is the region in which all the magnetic moments are aligned in one direction. That region is called domain. So it's nothing more, it's just that region is given that term domain. And then at the boundary of two different domains, we have domain wall, where in one domain the direction of magnetic moment is in along some one direction, in another domain the direction is somewhere else, and in the domain wall this is some significant thickness in which this the magnetic moments are actually from going from one direction to another. And then as soon as we come out of domain wall, all are in this direction. So we can go in detail, but again I don't think it's there for your undergraduate course. So but just for your knowledge, that we had discussed how domain formation why happens. Basically, to stabilize this, we discuss all the time that any system wants to get to a stable position, means it wants to minimize its energy. And as we had discussed, that if we have a material with all moments aligned same direction, so the exchange interaction energy will be very happy. Exchange interaction energy will be minimum, but because of all are aligned like this, we have north pole at one end, south pole at one end. So we'll have magnetic field lines emanating like this from this. And so as you can see here, inside the magnetic field line is going this way, outside is going opposite direction. So it's like it's trying to demagnetizing this sample. So this all the exchange interaction energy in this case is minimum because all moments are aligned in one direction. But because of this, we have these demagnetizing field which are demagnetizing the system, so increasing its energy. So to get rid of this situation, actually what happens in absence, if we are not applying any magnetic field, then what happens? Samples, depending on what type of sample it is, they form these closure domains so that there is no fields coming out outside like this, and there's no demagnetizing field. But here, as you can see, because they are not aligned parallel to each other, the exchange energy now increases. Exchange energy increases, but demagnetizing energy decreases. So all this domain formation is constantly a competition between exchange energy and demagnetizing energy mainly. Apart from this, there are other kind of energies also, but again, that is goes quite advanced, so we don't need to think. But yeah, so overall, it's very interesting, I would say, and usually at masters level we go in detail about domains and what kind of boundary this is. A lot of other things come here. Anisotropy energy, that even it depends on the material that in which direction it's easier for magnetic moments to align. Although we say when we apply some magnetic field, the moments tend to align along magnetic field, but it depends on the material. For some material, like we had studied in the beginning of this course, simple cubic, FCC, BCC structures. So it's seen that for some materials, some FCC material, maybe the magnetic moments tend to line along face diagonal or body diagonal, and for some BCC iron, it tends to lie along edge. So I mean that also. So there comes this anisotropy energy. So there's a lot of different energies result into what kind of domain will be there in a material. Because it's not something easy to calculate. But this is how we understand it, that all this gets decided because there is constantly the system is trying to minimize its energy. So if it thinks that by increasing some exchange energy, it can significantly decrease the demagnetizing energy, then it goes like this. So this was about domain wall formation, and yeah. Okay, so now next, the another thing that is especially getting very much important in current time is after, I don't know in which year, I forgot, but oh yeah, this also we'll discuss. Uh, so I don't remember which year, but it was some decades ago when a scientist, Kamerlingh Onnes, so while performing some, I'm not sure about the spelling, but some scientist, and he was doing some experiment with the helium gas. Okay, and so helium gas, we know at room temperature, normal pressure, it is a gas. So he was trying to liquefy it for doing some experiment. Usually we use nitrogen gas and helium gas. They become liquid at very low temperature. Like nitrogen gas becomes liquid at around 70 or 77 Kelvin. 70 or 77 Kelvin. Either of these, I'm not sure. Sorry. So we liquefy them and then we store them to cool other things. So helium gas cooling temperature at which it liquefies is around 4 Kelvin, I think. So he was cooling it to use it for something, and then what he saw, again, like many of phenomenon that we discover in science, many times it happens that it was accidental discovery. So this was also something similar, that what was observed, that so we know for metals or anything, as we go down in temperature, resistivity decreases. But because if some sort of impurity is there, then either it will become completely zero, or usually there is some residual resistivity is there, right? if its residual resistivity is always there, even in 0 Kelvin if you are talking about. But what he observed for this helium, that with as he was trying to liquefy it, that means by decreasing the temperature, resistivity was going down, and as soon as it reached below 4 Kelvin, suddenly the resistivity became 0. So usually for metals we see that either there is some residual resistivity or something, but we only see that only at 0 Kelvin all the vibrations will stop. No, there will be no thermal energy, and thus there will be no vibration, and thus only at 0 Kelvin, which is difficult to attain experimentally, it's very difficult to get absolute 0 Kelvin. But we just say that at that temperature it will be possible, there will be no thermal energy and no resistance because no vibrations will be there of atoms. But he saw that at 4 Kelvin for helium, at just before 4, just below 4 Kelvin, resistance suddenly becomes 0. And this again, we cannot measure exact 0.000 or some Kelvin, we cannot. But whatever was the limitation of the instrument, maybe up to maybe up to 2 second decimal digit or 4 decimal digit, that we don't know, but something. And then what he saw was that it was showing 0 resistivity. This was seen for helium, and then subsequent experiments were done with other metals, and it was seen that various such other, again I'm sorry I don't remember the names, there were other pure metals for which initially these experiments were conducted, and then seen for them also, as soon as the temperature came, there was some values which is called critical temperature. So don't get confused that Tc we were using to denote Curie temperature in the case of when we were studying magnetism, where Curie temperature was the temperature above which the ferromagnetic material becomes paramagnetic. Here this Tc, the same symbol we are using, but still just keep in mind this Tc is critical temperature. And this critical temperature, when we are talking about superconductors, so this critical temperature is the temperature below which the material becomes superconductor, means its resistivity becomes 0. And above it's just a normal material. And also it's seen that it's called superconductor because its conductivity becomes infinite, because the resistivity becomes 0, so conductivity is infinite. So it's not a normal conductor, it's a superconductor. That's why the name was given. But the interesting thing another was that it was not like only the materials which were conductor at room temperature, only they were becoming superconductor. Very interestingly, it was seen that even the materials which were insulators at room temperature, after going to very small temperature, whatever their critical temperature was, but again, this superconductivity phenomenon is not shown by all materials. It's not. They are very selective materials, and yeah, maybe we'll come to that later. So, I mean, this is very interesting that it's not like a normal conductor below some temperature is becoming superconductor. It's not like that. Even the materials which were insulating, electrically insulating at room temperature, below critical temperature, they were showing superconductivity. This was very interesting and bizarre also. And after that, there came some theories. Again, we don't need to go in detail for our understanding, but I'm just letting you know. There was like 3 scientists, Bardeen, Cooper, Schiffer. They gave the theory. So on their names, this is BCS theory, Bardeen, Cooper, Schiffer theory, where they talked about that there is electron pair, which we call Cooper pair, which is responsible for this kind of behavior. But because otherwise but that theory also is not able to explain the superconductivity that we see in some other kind of material. It could only explain it for some materials. So yeah, we don't need to go in detail about the theory, but this is basically what a superconductor is. And then again, another very interesting and important property that superconductors show is Meissner effect. Again, it's name of some scientist. So pronunciation, I'm not sure. Sorry. So Meissner effect. But what we can understand is the this. Um so what happens is superconductors are very good diamagnetic materials. That means diamagnetic materials, we know they tend to the magnetic flux density, magnetic field lines tend to avoid passing through them. Permeability is so small that they don't allow the magnetic field lines to pass through them. And superconductors are like very good kind of diamagnetic material because their permeability is zero, and so if you keep them in any magnetic field, H or B, I told you they are used interchangeably, so don't mind that. So if we keep in some magnetic field a superconducting material, then magnetic field lines will not pass through them. This is another very interesting property. Based on that, very interesting and useful um, applications have been exploited. If you know, okay, I'll show you one picture also. So based on that, this magnetically levitating trains, magnetic levitation, I'll show you the image. So if we have magnets, bar magnets, on top of that I am keeping superconducting material. First I need to cool it down because this TC that I'm telling you for superconductors, uh, that in fact this is very reason why we have not been able to use superconductors for applications at room temperature. Like if because see you anyone may think that if superconductors have zero resistivity, then why don't we use superconducting wires instead of the copper wire we use in our electrical lining? Because if we use superconducting material, then we'll be able there will be no resistance, no power consumption kind of situation. But the problem is this superconductivity till now, whatever different kind of material in which superconductivity has been found, all have critical temperature below room temperature. And room temperature, what we take usually 300 Kelvin. It may vary depending on season and place, but usually we take room temperature 300 Kelvin, which is around 27 degrees centigrade. And not just below, usually way beyond. Usually we are able to either we need helium gas to cool down such material to below their TC so that they start acting as superconductors. So like I mean just keep in mind these materials are don't show superconductivity at room temperature. Okay, we whenever we want to use their superconducting behavior, we need to cool them down below their critical temperature. That's why this critical temperature is very important, and only beyond that, below that, they show this. Like same we were talking about Curie temperature for ferromagnetic material, right? That beyond or above the Curie temperature, they will ferromagnetic materials will just behave like paramagnetic materials. So if we want to use their ferromagnetic property, we need to keep them under their Curie temperature. The same way for superconductors. But ferromagnets we see even at room temperature. Iron has a Curie temperature above 100 degrees centigrade or something. So even at room temperature we can have it, we can use its ferromagnetic property. But for superconductors, till now whatever superconductors have been explored, discovered, they all have critical temperature way less than room temperature. So usually some of them we cool down using helium gas because their TC is near 4 Kelvin, and usually we use nitrogen gas because its boiling temperature is 77 Kelvin or something. So it cools any material up to this. So one very famous like YbCO, it's very famously used for application. This is yttrium element, this is barium, cobalt, oxygen, and there is some particular combination O6 or something. When this is not a simple metal. This is I think it's a insulator at room temperature, and but below 70 Kelvin or something, it starts showing superconducting behavior. So I mean, all these are 70 Kelvin is means minus 200 degrees centigrade. You can think. Yeah, just to give you context, because 0 degree is 273 Kelvin. So when we are talking about 70 Kelvin, it means minus 200 degrees centigrade approx. So that much cool we have to make that material so that it starts showing superconducting behavior. So of course it's for our usual day-to-day application, we cannot provide it this cold temperature. That's why we are struggling to make application out of this. But if it would be possible, it would be very useful. So yeah, so magnetic levitation is what is one phenomenon shown by these materials. And in countries like Japan, we usually say they are trying to make maglev trains, where we'll have like the railway tracks will be like magnets, and on top of that these trains will be levitating. Means there will be no physical contact between the train's wheels and the railway track. And because there will be no physical contact, there will be very small resistance. I mean, there will be no resistance, and power consumption will be very small, and the speed can go to very great magnitude. But again, the temperature that we'll need to create here will be a challenge, because it's very low than room temperature. So yeah, what this magnetic levitation looks like is something like this. These are some bar magnets which are from which magnetic field lines are coming out. And because these superconducting materials, they don't let magnetic field lines pass through them. These are actually type 2 superconductors that again we'll see later. But yeah, so they just float here. They will not go anywhere. In fact, removing them from here also. Okay, when I'll explain you type 2 superconductor, that time I'll explain you why they are fixed. They are pinned. This is superconducting sample. This is just a normal bar magnet or something. So it has magnetic field lines around it, and these are usually type 2 superconductors. We'll see what is type 1, type 2 superconductor. And so magnetic field lines, some field lines are pinning this, so it will not go off track from this field lines also. Okay, but anyway, before that, so Meissner effect is what superconductors show this effect. And the Meissner effect is when superconductor expels, or they don't let the magnetic field lines to pass through them. When they are cooled below critical temperature, this line is written because a superconductor above critical temperature loses its superconductivity. So that's why when we want its any superconducting property to use, we need to keep its temperature below critical temperature. And so above Tc is just normal material, and that time magnetic field lines will pass through it depending its magnetic properties at room temperature, what it is. It could be ferromagnetic, it could be diamagnetic at room temperature, then again the situation would be different. So we don't know, because all sorts of materials are showing. As I said, it's not necessary that a material which is conductor at room temperature, that material only shows superconductivity. It's not like that. That's why we have not been able to explain the origin of superconductivity properly also. Because very different, some alloys, which is like mixture of some elements, they also show superconductivity. Some insulating materials show superconductivity at low temperature. So origin we don't know. So at room temperature, its behavior could be anything, but below Tc it shows superconductivity, and it becomes a perfect diamagnetic material and allows no magnetic field lines to pass through it. and thus Meissner effect makes the superconducting sample to levitate by repelling magnetic fields. Okay. Uh, yeah. So type 1, type 2 superconductor. As I said, we have some materials which above, when their temperature is above the critical temperature, they are in normal state. That could be anything, depends on what kind of material it is, but we say it's normal state. And when it is less than Tc, less than critical temperature, then only it becomes superconductor, like here. So this is the graph between temperature and magnetic field. So what happens, like we have critical temperature to define a superconductor, same way we have critical field also to define a superconductor. And actually there is a third parameter also, critical current density. So critical temperature, critical magnetic field, and critical current density, these three things have impact on the superconductivity of any superconductor material. Because like I explained, for that for any material to show superconductivity, it happens below some temperature. The same way, that's why we have some particular value which is we call critical temperature. The same way, the field that I am saying, that if we apply some magnetic field when it is in, when T is less than Tc, so the material is showing superconductivity, and I am applying some magnetic field. There is some critical value for this magnetic field also, up to which the superconductor will be able to expel the magnetic fields and still remain superconductor. But as soon as the strength of magnetic field crosses critical magnetic field value, then the material will lose its superconductivity. It will become a normal material. It has also been observed that not only temperature, critical temperature value, but critical field value also defines a superconductor. And again, that critical field value varies depending on what kind of material it is, like the critical temperature value differs. And similarly, we have current density. Now this is also like depends flux and lot of things, but I mean, if you are applying current to that material, then there is some current value. This current density is current per unit area. You can see if I understand. So I mean, some current value above which if you exceed, then that will also make the superconductor to lose its superconductivity. So these are these three, but here maybe it's again not important at your level. So we'll only talk about these two: critical temperature, critical magnetic field. These two. So the graph here is between this, and the area under this blue graph, this region, is the region in which the material is superconductor. And because it's superconductor in this region, so it can show Meissner effect, or it is in Meissner state, means it's diamagnetic. So this is 0. This material, say it's somewhere at this point, means its temperature is this and magnetic field around it is this. If I increase the temperature and take it above critical temperature, it will become normal. It will stop showing Meissner effect, means it will lose its superconductivity. If I keep the temperature same, temperature is very well below the critical temperature, but instead the field that I am applying, if I increase the field above this critical field value, okay, if the magnetic field that I am applying, that becomes more than Hc, even if the temperature is less, then again the material will become normal and lose its superconductivity. That is what this graph shows here, that when the magnetic field that I am applying to superconductor is below this critical field value, and when the temperature also is below this critical temperature, then only the
that particular system will remain in superconducting state or Meissner state. Otherwise, as soon as either magnetic field or temperature or both crosses exceeds these limits, they will become normal. They will lose superconductivity and they will just be in their normal state. Okay, so this was the graph. Even this graph is showing the same thing, but here you can see there is this Meissner state, which is like the proper superconductor, and then you can see there is something known as mixed state. This mixed state, I'll tell you what it is, and this is what differentiates between a type 1 superconductor and a type 2 superconductor. So type 1 superconductor is a superconductor which we were talking about here till H is less than critical field and T is less than critical temperature. Type 1 superconductor shows Meissner effect, but we have type 2 superconductor in which even if you exceed the field value, the Tc is same. But here what was happening in type 1 superconductor case, even if the temperature is less, as soon as you increase the magnetic field above critical field, it will completely lose its superconducting behavior. But in type 2 superconductor, these are some different kind of superconductors. Even if you increase the applied magnetic field beyond this critical field, so this critical field we call Hc1, because we have Hc2 also, second critical field. So when we cross this first critical field, immediately this material does not lose superconductivity. But what changes is that slowly it starts allowing the magnetic field lines to pass through them. So when it was here, the field was here, say the temperature I'm talking about is this, and the field is here. So somewhere it's the T and H is here. This time, when you apply field, it completely throwing out all the magnetic fields. This is what is happening here. But when the field that I'm applying, it crosses the critical field value Hc1, then slowly it starts allowing some of the magnetic field lines, not all. If all will start passing, then it will become normal state. But only few, like very small amount of magnetic field line, it starts allowing to pass through it. And this is why we call mixed state, because it's not properly superconductor because some field lines are passing now, and it's not completely normal state also because not all magnetic field lines it's letting pass through it. Only very small magnetic field lines are passing through it. So that's why it is called mixed state. I hope this is clear. And this mixed state is shown by some materials, and those materials are called type 2 superconductors. And the materials which do not show this mixed state, that means they do not have H2 critical field values, they are called type 1 superconductor. And what happens when, okay, I'm applying magnetic field more than this critical field value, so field lines start passing, and as I increase the magnetic field further, more it starts allowing more and more field lines to pass through it, and after the second critical field value, it completely loses superconductivity and becomes normal state. So I hope you understood this graph, and I hope you understood what I'm trying to explain, that we have two critical field values, Hc1, Hc2, when we talk about type 2 superconductors, and the differences, they have something known as mixed state. And because of this mixed state is what happens, that flux spinning, a phenomenon of flux spinning, that if you keeping in mixed state, then there is bar magnet, its field line is there, and this is my superconductor, and if the field I'm applying, this field that the bar magnet is applying is more than Hc1, then now the superconductor will be in mixed state. That means some field lines will be passing through it because of that, there is kind of pinning, means the superconductor gets kind of fixed to the bar magnet here. It will not go anywhere on its own, kind of. It will just stay there. It kind of get pins. So that's phenomenon of flux pinning. Flux pinning. Let me write it properly. Flux. The magnetic flux lines we are talking about, that gets pinned. So that's why we call it flux pinning. And this happens when superconductor is in mixed state. So of course this is seen for type 2 superconductors only, because type 1 superconductors do not allow any magnetic flux to pass at all. So type 1 superconductor, this is what we showed in last slide also, magnetic field lines and temperature on these axes. So as soon as we cross either critical magnetic field or critical temperature, the superconductor becomes normal material. Whereas for type 2, the TC, we have only one critical temperature, but we have two critical magnetic field values, HC1, HC2, or BC1, BC2, you can say. As soon as we cross this first magnetic critical value, it goes into mixed state. And then when we cross the second critical magnetic field value also, then it becomes a completely normal thing, even if the temperature is well below TC. So we have to keep in mind both magnetic field and temperature, and also, as I said, even current density. If there is some application of current, then that also we need to keep in mind, that even that current value should be less than the critical current density. Okay, and this is just how it looks like, that up to certain value, it should be, I think, temperature. I don't know why it's showing like this, and or it should be chi. Anyways, so, and this is how it looks. This is no, I think. Anyways, so with increase in critical field, there should be either TC here or HC here. Something is wrong. Anyways, so up to certain field, this is like type 1 superconductor has something like this, and whereas for type 2 superconductor, up to some value it shows superconductivity, then its diamagnetism starts decreasing and some of flux lines start coming in, and then some vortex structure. Actually, when we say that in magnetic field, this is some superconductor state in mixed state right now, if it is, then as I said, magnetic field lines, it starts allowing magnetic field lines. So it's like a cylindrical structure gets formed inside, not physically. Just like we know the any material is not uniform, there are some defects and lot of things. So just some defects start allowing passing of these magnetic flux, and these are called fluxons or vortex, so, and different names. And this is one thing. So yeah, I mean, so because superconductor tells us that it can have very good applications, it's a very popularly studied and being researched area in physics. But the challenges are this, that to create that much cold temperature, we need to put a lot of energy, lot of power. So even that is not very good situation. But people are trying these days to try out by making a lot of alloys or doping something, changing something about a material, so that the race right now is to get a superconductor at room temperature, so that we can use its, we can have its, I mean, we can use that material for some application without worrying about making, lowering the temperature. So that is one thing. Okay, and I think this should have been H and this should have been M axis. But more we do this, this should be minus M, that its behavior is diamagnetic, right? So the more for diamagnetic material we know, chi, which is m by h. The more we apply field, the more magnetization increases. But for diamagnetic material, we know this is minus m, this is h. As we apply the field, negative magnetization. So this is what it should be. As we apply positive field, there leads to negative magnetization because it's a diamagnetic material. And as we cross critical field, it loses diamagnetism, it loses any kind of magnetism, and it becomes normal state. The same thing here, H versus it should be minus M. As we apply field and it reaches critical Hc1 value, its diamagnetism starts decreasing. Why? Because now it starts, I said till here it's showing perfect diamagnetism. Means the material was completely expelling the magnetic field lines and not allowing any field flux to pass through. But as soon as we cross Hc1 critical field value, it starts, some of the field lines starts penetrating through the material. So the material is not perfect diamagnet anymore. So its negative magnetization starts increasing, and after Hc2 it's completely loses its diamagnetism. So yeah, this is how the graph should have been. Okay, so I think this much introduction about superconductivity is okay. Apart from that, there are a lot of interesting things about Josephson junction, Josephson effect, but again, I think not important for you. Now I think we can start discussing about numericals. So apart from some questions for superconductor only, I have kept some lot of questions on magnetism. They are very basic, but just to imbibe that, when we had introduction of magnetic properties of solids that time I told you the basic difference, how to understand what is H, what is B. But I also told you many times that very much these two terms are used interchangeably and they have several names also. The H, it's called magnetizing field, intensity of magnetic field, magnetization field intensity. Then B is called magnetic induction because it is the field that depends on the permeability of the material. It gets induced. So it's called magnetic flux density, magnetic induction, lot of different name this has. So how in a question you have to understand? Basically one thing would be to keep in mind their units, their dimensions. So for this, for B or magnetic field flux density, the SI units are Weber per meter square or Tesla. Whereas for this H, the field that we apply, magnetic field, magnetization field, intensity of magnetic field, it is either in CJ, it's Oersted or ampere per meter. So I mean they will be used interchangeably, but in question you should be able to identify them and then understand, okay, this is what is given and this is what we have to calculate. So just to get a hang of this, I have a lot of questions, basic, but just so that you will be able to understand in those questions that H is given or B is given or what we have to calculate, because that was also very important. So let's start with questions now. Okay, before questions, sorry, I wanted to tell you this is also very important thing. So because if some of you, if they are taking exam for this course and the exam for this course is going to be online, and how we get to know is, I think you all would have got this email. If you see this in this email, you would have got these email. So it's email from NPTEL. Type of exam will be available. So when you open this link, you will see this kind of, and when you will search for your solid state physics course, you will see this is online computer based. So you should if any of you is going to take up this exam, you should get hang of how to use the digital calculator. In the same email, I think you would have got, you can get this link. It opens the calculator that you will get to use, there. So because it's computer based online test, this is the, you cannot carry your usual physical calculator, the scientific calculator that we use. So you should at least in advance better to practice how this calculator works. There is the functions you will find, that is not the concern, but the thing is, like I'll tell you, in my physical calculator, if I want square root of 4, then first here I type the function square root, and then I type my number, which is 4, and then when I enter or when I press is equal to sign, I get the answer 2. So the function I put first, okay, what I'm telling is that the function, if I want square root of 4, so in my physical calculator, I choose the function square root and then I enter the number, and when I press equal to, I get the answer. In this calculator, what you have to keep in mind is, here you have to first take your number. You can see I pressed 4, 4 appears here. Then I have to take the, where is square root? This is cube root, yeah, this is square root of 4 2. So this you have to keep in mind, that in this digital calculators, you first take your number and then the function or the operation. Similarly, if you have to take sign of something, in physical calculator, we first press the sign button or that particular function button, and then we give the number. But here what you have to keep in mind is, first I'll clear that you have to take your number. Let's say, so right now it's in degree. This also please keep in mind, if it's taking right now in degree or radian. So this is 90, and because it's in degree, that means it is taking this as 90 degree, and then when I'll press sign, I'll get sign of 90, which is 1. I don't want to do that first press sign and then 1. No, it won't even wait. It's already given sign of the number that was already typed here, which was 1. So please keep in mind, otherwise this will put you into trouble that time, because we have habit of using our physical calculators. So there's high chance this, if you are straight away going to exam and then you encounter this difference, you will get confused. Maybe many times you will make mistake also. So that's why please keep in mind that this is one difference. Of course, otherwise the maths is same, but only thing you need to keep in mind is, in this digital calculator, what we have to do is, first we have to take our, enter the number, and then whatever function we want, the sign of 90. If I want to work with radian, then I'll take radian, and let's say I want to find out this is my number, and then I'll take sign of pi, which is 0. Or I have to take a cube root of, say, 64. So first I'll put my number and then I will give it the function. So it will take cube root of 64, which is 4. So this is very small thing, but it is very important, especially so that you don't get, you don't get confused in your exam that what is happening. So this is just a small difference, but very important to keep in mind. Okay, so please be aware of this, that in digital calculator you first put your number and then you press the function. This is very important, and this is different. So if you're going to take the exam for this course, I would say at least few days before, start practicing on this digital calculator to do these calculations, so that you get used to, habituated of this difference. And this was the only thing I wanted to tell, because we also don't know much detail about the pattern of exam or anything. We are only teaching assistant. We only take classes for this numerical problems. We have not any idea about the patterns or anything, but this is one thing about digital calculator that I wanted to tell you. And for you, it's going to be online, so you need to use this calculator only. You cannot take your physical scientific calculator in the exam hall. So please keep this in mind. And now we can start doing our, and I'm sure you would have got these emails, otherwise these are the links. This is the link for that spreadsheet which tells you what are the different courses which are online based or paper based, and this is the link in that email itself which takes you to this digital calculator where you can practice. Okay, with this, now let's move on and start doing some numerical problems. As I said, I'm giving you some lot of questions to so that you understand the difference, or as I said, they use H symbol and B, even their terms sometimes interchangeably, but you have to identify in the questions. My hint is to consider the unit they are talking about. That's like big hint that if they are referring to H or B. Okay, like here for this question, a paramagnetic material has magnetic field intensity. We had discussed that magnetic field intensity is H. This is the field that we apply. But still, if you have any confusion, look at its unit. It's ampere per meter, which we know is for this. Because it is the current that we apply and the dipole moment that is generated because of it. So that comes in ampere per meter. You have to remember these things. That for this it's Weber per meter square or Tesla. For this it is Oersted or ampere per meter. In CGS and SI unit, we have different units. But if you at least identify or keep in mind these SI units, you will be able to understand if they are talking about B or they are talking about H. Okay, because this is what is given and they will ask you to maybe calculate the other thing. So that's why it should be clear to you. Okay, so here magnetic field intensity, we know it's H. Also its unit is ampere per meter. That means it's H they are talking about, and the value is 10 to the power 4 ampere per meters. This is in SI unit. If the susceptibility of the material at room temperature is 3.7 times 10 to the power minus 5, calculate the magnetization M and flux density. Flux density means B in the material. So magnetization, we already know these are very trivial formula. This is, so let's calculate magnetization. Chi times H, susceptibility times the magnetic field intensity or magnetizing field, different names but refers to H. Chi is 3.7 times 10 to the power 5 and H is 10 to the power 4 ampere per meter. So magnetization will be 3.7 times 10 to the power 9, and magnetization SI unit will be ampere per meter also. Either it goes EMU per cc or okay. So calculate magnetization. Magnetization will be this ampere per meter, or yeah, and B. Now magnetic flux density formula is mu naught M plus H. This permeability of free space, this value is 4 pi into 10 to the power minus 7, and M is 3.7 into 10 to the power 9. H is 10 to the power 4 ampere per meter. So when we will calculate this thing, the answer will be B will be 4 pi and this. This will be 10 to the minus 7 minus 2 and this will be minus 3. Calculate. 4 times pi answer will be 0.0126 Weber per meter square. Oops. This will be the magnetic flux density. So this is the answer. So we had to calculate magnetization and magnetic flux density. Next question, let's see. A magnetic material has magnetization. So here magnetization is given and it is 2300 ampere per meter and produces flux density. Flux density means B, and from unit also you can see Weber per meter square. So it is B, 0.00314 Weber per meter square. Calculate the magnetizing force. Here they are calling it magnetizing force. Otherwise we call it magnetizing field. What we are referring to is this H. This actually I every time put this is vector. We use it a lot, so that's why I always keep vector symbol, but just H is okay. And relative permeability of the material, mu r, also we have to calculate. Let's first calculate H. Since we know B is mu naught M plus H. So we have B, we have M, mu naught is a constant, we know the value. We need to find out H. So after rearranging this formula, H will be B divided by mu naught, right, and minus M. Here putting the value 0.00314 divided by 4 pi into 10 to the power minus 7 minus 2300 ampere per meter. When we will do this calculation, we will get 198.7326 ampere per meter. This will be the magnetizing force or the magnetizing field in ampere per meter. And relative permeability of material, mu r we have to calculate. So mu r, let's do it here. The relation between susceptibility we know is M by H, right? And susceptibility we know, relation between permeability and susceptibility is this. This is not given, but M is given, and we have calculated H. We have calculated this. We can get this, and this is also related, this is also related, means from this equation 1 and 2, M by H is equal to mu r minus 1. We have to calculate mu r. So mu r, which is relative permeability, it will be M by H plus 1. M we calculated, M is given 2300. H we have calculated, which is 198.7326 plus 1. And we do this calculation, 2300 divided by 198.7326 plus 1 is 12.573. This is permeability, magnetic permeability value. So this is the answer. Next question. A paramagnetic material has FCC structure with cubic edge. So we have a paramagnetic material which is FCC and its cubic edge, that means the lattice constant A is 2.5 angstrom. If the saturation value of magnetization, that means the magnetization is given, is 1.8 times 10 to the power 6 ampere per meter, means the maximum magnetization of this material is this, calculate the magnetization contributed per atom. So the maximum magnetization or the saturation magnetization, we know this word, right? That when all the magnetic moments are in the same direction, then that time the magnetization of the material reaches the maximum value possible. So that is why they have used saturation value of magnetization. So it is the maximum magnetization possible for this material is this value, and we have to calculate per atom the magnetization and in terms of Bohr magneton. So let's do this. So magnetization, the total magnetization will be magnetic moment of one atom or one dipole into number of atoms per unit volume, right? Here this is given, number of atoms per unit volume we'll find out because we know FCC has, we can calculate how many atoms are there in FCC, and volume we can calculate from this. So number of atoms per unit volume we'll calculate. Magnetization is already given, the saturation magnetization. So we'll be able to calculate the magnetic moment of one atom. So let's calculate number of atoms per unit volume. So in FCC we know that we have 8 atoms in the corner which contribute total 1 atom, and we have 6 atoms on 6 faces which contribute total 3. So 3 atoms from the faces, 1 atom from the corner, that means we have total 4 atoms in FCC. And then when we go for this volume, then we have to take, this is number of atoms, and then volume will be A cube. So this will be 4 divided by A cube, 2.5, and angstrom is 10 to the power minus 10 meters. So cube of this. When we calculate this, or we can just simply directly put here. So magnetic moment will be magnetization divided by this. Magnetization is 1.8 times 10 to the power 6 divided by this, means multiplied by 2.5 cube 10 to the power minus 30 divided by 4. This will be 1.8 multiplied by 2.5 divided by 4. This will be 7.03125 into 10 to the power 6 minus 30 means minus 24. Now this is in some ampere per meter square, okay, right now, and we have to answer in Bohr magneton. Now we know 1 Bohr magneton value is 9.27 times 10 to the power minus 24 ampere per meter square, and the magnetic moment of one atom is this. So if I divide it by the value of Bohr magneton, then I can get the value of the magnetic moment of this one atom in terms of Bohr magneton. So that magnetic moment in terms of Bohr magneton means I have to divide 7.03125 multiplied by 10 to the power minus 24 divided by this value of 1 Bohr magneton, is 9.27 times 10 to the power minus 24. So answer will be, let's see what this is, 7.03125 divided by 9.27. It will be 0.7585 Bohr magneton. This will be the answer. Okay, next question. Saturation magnetic induction. Magnetic induction word has come. It should be this. and then we look at the unit, that is Weber per meter square, means they are talking about B. The value is 0.65 Weber per meter square, and it's the saturation magnetic induction. If the density of nickel is 8906 kg per meter cube and atomic weight is 58.7 gram per mole, of course, calculate the magnetic moment of nickel atom, again in Bohr magnetron. So we have been given the saturation magnetic flux density. We know saturation magnetic flux density is number of atoms per unit volume multiplied by permeability of free space and then dipole moment of the material. If not, don't get confused. So B we know is permeability and then the field we are applying, and or the magnetization. Magnetization will be number of atoms per unit volume and magnetic moment. Okay, let's not get confused, but this is permeability. Okay, so a number of atoms per unit volume we need to calculate. That will be density multiplied by Avogadro number divided by atomic weight, and this, keep in mind, usually Avogadro number is per mole. Here we have to consider gram per mole it is. Here we have to consider kg. So this will be density is 8906 kg per meter cube. Avogadro number 6.023 times 10 to the power 23 usually it is. But atomic weight, which is 58.7 gram per mole, when I will convert it into kg per mole, it will be per 1000. So 10 to the power 3 more will come. When I will do this calculation, my answer, okay, let's see what is the answer. Number of atoms per unit volume 8906 multiplied by 6.023 divided by 58.7, so it is 913.81, 10 to the power 26 atoms per meter cube. Now I need to calculate this. This is done. This I know. This I will get. This is given. So dipole moment will be B divided by N and mu naught. So this value 913.81 times 10 to the power 26. No, sorry. B is 0.64. 0.64 Weber per meter square. In the denominator, we have 913.81 times 10 to the power 26. And mu naught is 4 pi times 10 to the power minus 7. So when I'll do this, the value I'll get is 5.66 times 10 to the power minus 24 ampere per meter square. Now my answer, they have asked in Bohr magnetron. So again I will divide this by 9.27 times 10 to the power minus 24, and when I do that I will get my magnetic moment in terms of Bohr magnetron, and the value will be 0.61 Bohr magnetron. This will be the final answer. Next question. In a magnetic material, the field strength is found to be 10 to the power 6 ampere per meter. Magnetic field strength, they are talking about this. They are talking about H, and the unit is ampere per meter. 10 to the power 6. So I hope now you are able to identify they are talking about they are talking about H or B or N also. Okay, if the magnetic susceptibility of material is 0.5 times 10 to the power minus 5, calculate the intensity of magnetization. Calculate the intensity of magnetization means we have to calculate this, and flux density in the material. Now intensity of magnetization, chi times H. This will be 0.5 times 10 to the power minus 5 multiplied by 10 to the power 6. This will be 0.5 times 10 means 5 ampere per meter. And we have to calculate flux density in the material, means we have to calculate B, which is mu naught M plus H. Mu naught we know 4 pi times 10 to the power minus 7. M is 5. H is 10 to the power 6. When we will calculate this, 20 pi times 10 to the power minus 7 plus 4 pi times 10 to the power minus 1, and we will do this. When we will do this calculation, we will get B is equal to 1.257 Weber per meter square. Yeah, this will be the answer. Next question is on superconductors now. A superconducting tin has a critical temperature of 3.7 Kelvin. At zero magnetic field. Because I told you with critical temperature, critical field is also important. And a critical field of 0.0306 Tesla at 0 Kelvin. You can use B also if you think it's in Tesla, but I told you it's not a big deal. Anything is fine. As far as we are doing the calculations correct and taking care of all the constants. You can use B symbol or H symbol, it's okay. Okay, so this is given, we have to find the critical field at 2 Kelvin. So why the critical field value will change at different temperature, I'll show you in the graph. Like here, for this temperature, the value of critical field is this, but at this temperature, you see the critical field value has changed. So if your temperature is higher, then your critical field value will decrease. If you further increase your temperature, then critical field value will even more reduce. So that's why in this question, they have given critical field value at 0 Kelvin and they have asked to calculate critical field value at 2 Kelvin, because at different temperature the critical field value changes, as I showed just now in graph. I mean, just to draw it again, if this is T, this is H, then at different temperature the value of critical field will change. When the temperature is this, critical field value will become this. When temperature is here, critical field value will be here. So they have given critical field value at 0 Kelvin. They have asked us to calculate critical field value at 2 Kelvin. Okay, so the formula for this thing is, we have straight formula for this, that magnetic critical field value at whatever temperature you want to calculate. For that, you need critical field value at 0 Kelvin, that we denote by H naught. So this is the critical field value at 0 Kelvin. And then you need 1 minus T by Tc, critical temperature, and the temperature at which you want the magnetic field value, that square of this. This is a straightforward formula you can use for all these questions. So this is what we have to calculate at 2 Kelvin. So we want to calculate this at 2 Kelvin. H naught, that means critical field value at 0 Kelvin, is 0.0306. 0.0306. 1 minus T is 2 Kelvin. Tc is, critical temperature is 3.7 Kelvin. we have to take square of this when we do this calculation. So what is 4? 2 divided by 3.7, 0.29, 0.7 multiplied by 0.0306. The answer is 0.0216. 6 Tesla. Because they had given the answer in Tesla, so what we calculate is also in Tesla. So either you can use B symbol or H symbol, that's up to you. Okay, this is the answer. Now next question. Again, it's on superconductor. Calculate the critical current and current density for a wire of a lead having diameter of, we have been given diameter which is 1 mm. We have to calculate critical current and the critical current density at 4.2 Kelvin. Critical temperature is 7.18 Kelvin and the field that they are applying is 6.5 times 10 to the power 4 ampere per meter. So the formula to calculate critical current, like I gave you the formula to calculate the critical magnetic field. So the direct formula is this. You need 2 pi r and critical magnetic field value you need. Okay, 2 pi and radius is, diameter is given 1 mm, means radius is 1 mm by 2. It means 0.5 mm, and mm if you will convert to to meter, it will be 10 to the power minus 3. And Hc, this is the critical field value, critical temperature, and this is critical field. They have not mentioned, but this is critical field. Is 6.5 times 10 to the power 4 ampere per meter. When we will do this calculation, answer will be 2 times pi times 0.5 times 6.5 is 20.42, and minus 3 plus 4 means 4 minus 3 is 1. That means okay, so this is 200.42 ampere is the critical current, and critical current density will be just the current per unit area. So critical current divided by area, which will be pi r square. So this will be whatever we calculated divided by pi r square, 200.42 divided by pi, and r is 0.5 10 to the power minus 3 square. 200.42 divided by pi divided by this answer will be 255.18. I'll go to next. 255.183, and the powers will be 10 to the power plus 6 ampere per meter square. Okay, this will be the critical current density value. If you want to move the decimal, then it will be 2.55183 times 10 to the power 8 ampere per meter square. This will be a critical current density value. Next question, prove that susceptibility of a superconductor is -1 and relative permeability is 0. Okay, so we know whenever we apply magnetic field, magnetizing field to any material, depending on permeability of that material, magnetic flux density is induced, right? So, and the relation between them is, if it's yeah, either we write the this, and what is this? It incorporates, when we incorporate this, this is permeability of that material. In terms of permeability of free space, we write it like this, right? 1 plus mu1. Okay, so this is one relation, and we know superconductor, if we are talking about type 1 superconductor, or not mixed state but perfect superconducting state, then it's a diamagnetic material. That means no magnetic flux density is inside the superconductor. So we can set B0, and then this will become like this. That means this will become 0. So M is equal to minus H. Now we know chi is M by H, and M is minus H. That means -1. So we have shown that for perfect superconductor, susceptibility is -1, and permeability, so the relation between susceptibility and permeability is this. Now susceptibility is -1, means -1 is equal to mu r -1. That means mu r is equal to 0. That means for a perfect superconductor, susceptibility is -1 and permeability is 0. That we have shown. Okay, next question. Find the critical current which can pass through a long thin superconducting wire. So we have to find the critical current which can pass through a long thin superconducting wire of aluminium of diameter 2 mm. So radius will be 1 mm, and in meters it will be 10 to the power minus 3 meters. And critical magnetic field value is 7.9 times 10 to the power 3 ampere per meter. Okay, you have to find the critical current value, and I told you the direct formula to find out the critical current is 2 pi r Hc. That means 2 times pi times radius, which is 1 minus 3, and Hc is 7.9 times 10 to the power 3 ampere per meter. When we will calculate this, it will be 2 times pi times 7.9. It is 49.6372, and the powers will be 10 to the power 0. So this is 49.6372 ampere. This is the correct answer. Next question. The superconducting transition temperature means it is the critical temperature only. Transition temperature is the critical temperature below which it transitions into superconductor, above which it transitions into normal material. So they are referring to critical temperature only, is 7.26 Kelvin, and initial field at 0 Kelvin is this. Calculate the critical field value. You have to calculate critical field value, and the initial field, that means at 0 Kelvin, the initial field at 0 Kelvin means the critical magnetic field value they are telling at 0 Kelvin. That is 64 times 10 to the power 3 ampere per meter. So we know direct formula for this also. Hc that they want us to calculate, because they want us to calculate it at 5 Kelvin. Okay, they want us to calculate at 5 Kelvin. The formula H naught 1 minus T by Tc square. H naught is 64 times 10 to the power 3. 1 minus T is 5 Kelvin, square of it 25. Tc is 7.26, square of it. Let me just write 5 square and 7.26 square. When we'll do this, we'll get answer 33.644 and power will be 10 to the power 3 ampere per meter. This will be the answer. Okay. Next question. Magnetic field strength of silicon. Magnetic field strength of silicon. This is H. 1500. Also you can see from this unit, ampere per meter. If the magnetic susceptibility is minus 0.3 times 10 to the power minus 5, calculate the magnetization. This we have to calculate. And flux density means this we have to calculate. So M we know is chi times H. That means minus 0.3 times 10 to the power minus 5 times 1500. This will be minus 4.5 times 10 to the power minus 3 ampere per meter. Okay. Straightforward multiplication. And then B is mu H, and mu will be actually 1 plus chi is the relation, so it will be chi is this, so 1 plus chi that we can put directly here. 1 plus chi is this 1 minus 0.3 times 10 to the power minus 5 multiplied by H, which is 1500. So we'll get B. Let's do this. 0.3 times 10 to the power minus 5. Multiplied by 1500. It means the answer is 1499.9955 Weber per meter square. This is the correct answer. Next question. Calculate the critical current density. Calculate the critical current which can flow through a long, thin superconducting wire of diameter 1 millimeter. Critical magnetic field is 7.9 times 10 to the power 3 ampere per meter. We know straight formula 2 pi r times hc. 2 times pi times r is 0.5 mm, and in meters it will be this. Hc is 7.9 times 10 to the power 3. We will multiply 2 times pi times 0.5 times 7.9. Is it repeated the question? I don't know. But anyways, 24.806, and the powers will be gone. So this ampere will be the correct answer. Questions, let's finish and then we will be done. Calculate the critical current. Again, that's similar question. Critical current, we have to calculate the critical current at 0 Kelvin for a long wire of lead which has circular cross section, radius 5 millimeter. Critical magnetic field is 8 at 0 Kelvin is 803 times 10 to the power minus 4 Tesla. We have to calculate critical current. Critical magnetic field is given, critical current we need to calculate. Again, the same formula. 2 pi r hc. Oh, so they have given it in Tesla, means they have given this. So we know we can use this relation since B is For this we can use this relation and we can use mu naught. That means this will be 2 pi r. BC is given. We need to find out HC means B by mu naught. Okay, we can use this. 2 times pi times radius is 5, 10 to the power minus 3 meters. B is 803 times 10 to the power minus 4. Permeability of free space 10 to the power minus 7. And we'll calculate this. We'll get 2007.5 ampere. This is the correct answer. Okay, another question. I think this is the last question. Calculate the critical current density at 4 Kelvin for a long superconducting wire which has a circular cross section of radius. Almost same question. This is 5 times 10 to the power minus 3 meters. Critical field for superconducting wire. Critical field is in Tesla, means this is given. Critical field is 8 times 10 to the power minus 3 Tesla. Critical temperature is 7.2 Kelvin. We have to find out critical current. So you can critical current density we have to calculate. I think we can directly use our formula. Critical current and critical current density. Okay, so the thing is critical field for superconducting wire, and this is given at 0 Kelvin. Okay, and we have to find out critical current density as 4 Kelvin. Now we know critical current density I can calculate from critical current, and critical current, to calculate this I need critical field at 0 Kelvin. But here I am given, I have to calculate at 4 Kelvin. That means to calculate critical current at 4 Kelvin, I need critical field at 4 Kelvin. But they have given the critical field at 0 Kelvin. So first I need to calculate the critical field at 4 Kelvin. After that I can use that to calculate critical current at 4 Kelvin. Okay. So we know in terms of HC and B, the formula will be same because B is mu naught H. So at 4 Kelvin it will be, so what the value is at 0 Kelvin, 1 minus T square by Tc square. This at 0 Kelvin, 8 times 10 to the power minus 3, 1 minus T square. T, the temperature that we are interested is 4 square. Tc is 7.2 Kelvin, so square of that. When we'll do this calculation, we'll get 5.53 times 10 to the power minus 3 Tesla. So we calculated this. Now to get HC will be BC divided by mu naught. And then we'll put that here. So IC will be 2 pi r, and HC I told, HC will be BC divided by mu naught. This will be 2 pi r BC divided by mu naught. Now this HC and BC at 4 Kelvin, so that I get IC at 4 Kelvin. This is not multiplication, I am just telling IC at 4 Kelvin. So this will be 2 times pi times r is 5 millimeter. That means 5 times 10 to the power minus 3. And BC I got 5.53 times 10 to the power minus 3. 5.53 times 10 to the power minus 3. And mu naught is 4 pi times 10 to the power minus 7. When I will calculate this, I will get 138.25 ampere. And I have to calculate critical density at 4 Kelvin. It will be IC divided by area, pi r square. 138.25 divided by pi times 5 times 10 to the power minus 3 square. And after calculating this, we will get answer 1.76 times 10 to the power 6 ampere per meter square is the critical current density. So keep these things in mind. I mean, by mistake don't use this value, because this is at 0 Kelvin and we have to find out the value at 4 Kelvin. So first use this relation to find the magnetic critical field value at 4 Kelvin, then use it to calculate critical current at 4 Kelvin, and then ultimately the critical current density at 4 Kelvin. So this is the correct answer. I think these were all the questions, and thus I think all the sessions for this NPTEL course finishes here. If you still have doubt, you guys can put in our discussion group, and you had good time learning in these courses, and I could be of some use. I tried to bring as many numerical problems possible and some important concepts that I thought I should repeat. I did that. So I hope you found this course useful. With that, let's finish this session. Thank you.